problem for us. I think I'm running out of time. I'm over time, I guess. When am I supposed to finish?
It's okay.
A few more minutes?
Yeah.
Okay. I wanted to say a little bit about fission and fusion because I've talked about, efficiency and renewables and sequestration. So in terms of fission, this is the first thing falls into actually very much the same category as energy efficiency, which is something that comes almost at negative cost, and that is extending the operation of today's nuclear power plants. Nuclear essentially has a capital cost, but a very low operating cost. Nuclear is not troubled at the moment by the price of uranium. Nuclear is troubled by the capital cost of nuclear power plants and how long it takes to build them and the interest rates associated with borrowing that money and not getting any income until the plant is finished. And so if you've already got nuclear power plants, and this is certainly the case in the US, Europe, and Japan, if you can safely extend their life, there's a tremendous benefit there, especially if it's hard to build new ones, which is the case in a lot of places right now. So that's something that can help. You can think about uprating the power. There's actually been a lot of generating capacity put onto the grid in the US from nuclear power without building any new plants because the plants have all had power uprates. And that's a form of energy efficiency, really. Now, even with extending the life of the plants, you have some challenges. In many countries, it's not yet agreed what to do with the spent fuel. That's not fundamentally a technological problem. It's a very real social problem in many countries. You've got to understand what happens to the materials inside the plant, the structural components, as they age, as they're exposed to high radiation environments. And you'd like to be able to understand how that translates into safety margins over time. And for that, we actually have some pretty powerful tools now. This shows the results of some simulations that we've been doing using our supercomputers to explore pressurized water reactors. There's a project that we're involved in called the Consortium for the Advanced Simulation of Light Water Reactors, which is using supercomputers to do very high fidelity simulations. This shows basically this is a quarter cross-section through the core of a Westinghouse pressurized water reactor. And this is one of the individual fuel channels within it. And the point is that we're able to do full-up simulations of the whole reactor, but see some of the fine scale of the differences between the different channels and what's happening to the heat flows and the materials, the fuel behavior, neutronic performance, all in a single coupled simulation. And this is going to be extremely valuable for thinking about how to extend the life of the plant, how to go to higher burn-up fuels. Longer term, you'd like to transition to what are called inherently safe reactor designs, where they don't need active intervention in order to maintain a safe condition. And this is what people talk about when they talk about so-called Gen 4 plants, inherently safe reactor designs and sustainable fuel cycles, the kind of closed fuel cycles. So that's some of the R&D challenges there. And with fusion, and I think I'll stop here since I'm getting a little bit over time, the near-term challenge is to understand whether or not this is feasible. And that's still fundamentally a science question. And there's a project that's being pursued called ITER, which is an international undertaking being built in Cadarache in France, but involves not just the EU, but the US, China, Japan, Russia, India, and South Korea. EU is providing 45% of the cost because it's in France. The other countries are all providing 9%. It's a massive experiment. Actually, it turns out it's a massive experiment, not just in fusion, but also in managing a project in an international context of extraordinary complexity. And so it turns out the second challenge may be harder than the plasma physics challenge. But the goal is to sustain a burning plasma for about 500 seconds and explore the physics of that. If you can do that, then you encounter a new set of problems when you start thinking about fusion power. Is, okay, I can make the fundamentals work. Can I develop the materials that will survive in that kind of environment in a realistic fusion reactor? So immediately upon solving the physics problem, you confront a materials problem. Now, Part of the solution to the physics problem, at least, will be the theory, modeling, and simulation of the behavior of this plasma, which is something that we're making very good progress on. And I think at this point, I probably better stop and see if there are any questions.